Question 1. What is the principle of operation of guided wave radar? Answer. Radar level measurement technology can be broken down into two different categories: pulsed and frequency modulated continuous wave (FMCW). An advantage with pulsed technology is that it requires less processing power. Therefore, most two-wire gauges use this technology. An advantage with FMCW is that higher accuracy can be achieved, but more processing power is required, and therefore FMCW radars are typically 4-wire. In pulse transmitters, the level measurement is a function of the time taken from the radar signal to travel to the surface and back. In FMCW gauges, the transmitter constantly emits a swept frequency, and the distance is calculated by the difference in frequency of emitted and received signal. Question 2. Are radar gauges safe? Answer. Yes. The emitted signal is less than 3% of maximum leakage allowed from a microwave oven. Radar waves are of no greater intensity than the constant radio, cellular and other communication waves that surround us every day. Furthermore, the transmitter is normally placed in a metallic tank that acts as a Faraday's cage, and therefore the radar waves are isolated within the tank. Question 3. What is the difference in frequency between pulsed technology guided wave radar and non-contacting radar? Answer. With guided wave radar, the pulsed microwave are guided down the tank by the probe, making it less sensitive to disturbances than free propagating microwaves. Pulsed non-contacting radar uses a carrier frequency, for example 6Hz 5401 Rosemount or 26Hz 5402 Rosemount, to carry the microwave, which are radiated into the tank with an antenna. Question 4. Why should we use radar technology? Answer. The radar signal is virtually unaffected by the tank content and tank atmosphere, temperature or pressure. The measurement is not influenced by changing material characteristics such as density, dielectric properties and viscosity. Since there are no moving parts, the transmitters are virtually maintenance-free. All of the characteristics above make radar a very useful and fast-growing level measurement technology. Question 5. How does the frequency of the radar affect the measurement? Answer. A higher frequency provides a more concentrated narrow beam, which can be useful in applications where there are obstacles present in the tank such as manways, agitators or heating coils. The downside of high frequency is that the measurement is more affected by vapors, dust and product buildup on the antenna. Low frequency radar, which have a longer wavelength and wider beam angle, tends to cope better with steam, dust, condensation, contamination and turbulent surfaces. Question 6. In what way does the dielectric constant DC of the media affect the measurement? Answer. Electromagnetic energy is emitted from all radar devices. When the emitted signal reaches a point where there is a change in DC, usually the media surface, some of the signal is reflected back to the transmitter. The amount of energy that is reflected back to the transmitter is proportional to the DC of the media. A rule of thumb is that the value of the dielectric constant represents the percentage of energy that is reflected. Thus, a DC of 8 means that 8% of the emitted energy is reflected back to the transmitter. Fundamentally, media with a higher DC provide stronger return signals and are therefore easier to measure. Question 7. Does radar work on foam? Answer. The effects of foam on a radar measurement can be difficult to predict. In some applications, the foam may dampen out the signal completely, while other types of foam may be transparent to the transmitter. The thickness, density and the dielectric constant are factors that need to be considered when evaluating an application with foam. On dry foam, the microwaves typically passes through and detects the liquid surface below. On medium type foam, the signal can be absorbed or scattered, and the results are therefore hard to predict. If the foam is wet, the microwaves are often reflected from the foam surface, and thereby the foam surface level is measured. The frequency at which the radar operates also affects how foam is measured. Low frequency radar 5 GHz in general penetrates foam to a larger extent than high frequency 20 GHz radar. Guided wave radar is in general better suited to measure on applications where foam is present. Sync-AT radar uses a lower frequency pulse. Question 8. Are there any restrictions on what steel pipe material can be used? Answer. Any type of conductive material can be used as long as it is compatible with the process media. If the material is not conductive, it will be transparent to the radar beams and therefore it will have no effect. Question 9. Will two or more radar units in one vessel conflict with each other? Answer. The signals from two or more transmitters in one tank will not blend and therefore the radar units will not conflict with each other. If it concerns two or more 3300s, the rules for nearby objects would apply to the probes as they do to other metallic objects nearby. For that reason, the probes need to be installed a certain distance away from each other. Question 10. Will radio noise or other interference cause problems? Answer. The transmitters use a specific narrow frequency and are therefore not prone to disturbances from other sources. It is very uncommon with disturbances, and it is rare that the disturbance source operates at precisely the same frequency as the transmitter. Furthermore, the transmitters are often installed in metallic tanks that provide a Faraday's cage which prevents electromagnetic disturbances from the outside to enter the tank. With guided wave radar, if disturbances are present in tank, the coaxial probe are recommended, since the radar signal travels inside of the pipe undisturbed by the interference sources on the outside. Question 11. Are there any restrictions on the nozzle height? Answer. Since the nozzle, and especially the lower end of the nozzle, can create interfering echoes, it is recommended that the height of the nozzle is kept within certain values depending on the type of probe, antenna and type of transmitter that is used. For detailed information regarding these values, please refer to the product data sheet and reference manual for each transmitter. Question 12. Are there any restrictions on the nozzle diameter? Answer. In conjunction with the above statement, the nozzle diameter also affects the measurement, since a diameter nozzle that is too small will create disturbance echoes. For detailed information regarding these values, please refer to the product data sheet and reference manual for each transmitter. Question 13. Are there any restrictions when measuring instilling pipes? Answer. Pipes should be an all-metal material. Non-metallic pipes or sections are not recommended for non-contacting radar. Plastic, plexiglass, or other non-metal materials do not shield the radar from outside disturbances and offer minimal, if any, application benefit. Other requirements include: pipe should have a constant inside diameter. Pipe must be smooth on the inside. Smooth pipe joints are acceptable but may reduce accuracy. Avoid deposits, rust, gaps, and slots. One hole above the product surface. Minimum hole diameter is 0.25 inches 6 mm. Hole diameter O should not exceed 10% of the pipe diameter. D. Minimum distance between holes is 6 inches 150 mm. One hole should be drilled on one side, and the bird, ball valve or other full valves must be completely open. Failure to follow these requirements may affect the reliability of the level measurement. See Technical Note 00840 to 0300 to 4024 Guidelines for choosing and installing radar instilling wells and pipes for more information.